You said early stage, design stage, it is better to consider the application of a supplementary damping device. I agree with you so much. But not only one device. In recent trend in Japan, early stage of application of damping devices in Japan, on one damper to one building. But now, in these 10 years or so forth, trend is like this. Multiple different types of damper are used for one building for different purposes. That will be more robust and also more efficient.
Yes,
I think.
Yeah, agree. Yeah. Normally when we control the wind, and sometimes there's consideration in China. We discussed this before. We use a distributed damping system. Like this morning, we have discussed. For like in my presentation, in China, this is restricted for the building deflection, the wind drifting. They control this drifting angle by 1 to 500. And basically, when recently we did one project, we look at different approach. One is use a TMD and TSD. Another one looking at distribute damper. And with distribute damper, sometimes work really well for earthquake. Yeah, but for wind, because this deformation is really limited, it's really restricted. In China, we found that distribute damping system is hard to apply because the angle and displacement requirement.
It's just a question for Kevin. For natural ventilation, you mentioned temperature range for optimal comfort, but I was just wondering if humidity comes into play as well.
Yes, so it's. I probably should expand on that. With regards to the temperature range itself, the psychometric chart actually takes into account both the humidity factor, so it's at apparent temperature. So it's not purely just the temperature itself, it's humidity that does impact that. So obviously that's where you have the big influences from the sites. So you can't just apply the same sort of concepts for every place around the world. You need to consider the actual location of the project and how that influences what would be viewed as a comfort. And that obviously change throughout the year as well. So you might have a different scenario for the winter periods as opposed to the summer case as well.
With the wind speed in strongest in recorded history, just like the super typhoon we had in the Philippines, 320 kilometers per hour. Gustiness was 350 kilometers per hour. And our building code requires only 220 kilometers per hour. Can wind engineering address the hazards before they become disasters? Or we just depend on disaster insurance? Yeah, thank you.
So actually, in my report, one level above does not mean that my data is actually extends the Chinese code. Actually, it's just that our data is larger than the data from the weather station.
So the actual wind speeds that we design for typically are based off some sort of data set or some sort of large-scale modelling that we've been able to utilise. A perfect example is just recently in Australia they've been looking at the actual difference between the way the wind speeds themselves are measured and what the actual sampling rate is and what impact that has on the wind speeds. So I think it's something that we need to continue as a wind engineering community is to continue that that push to make sure that as more data and sort of long extended period of sample that we can actually utilise to analyse it is then incorporated back into the standards so that provides the sufficient amount of design wind speed that we're utilising, because that is something that is a concern. Perfectly recent example is in Dubai, the Dubai code, all the wind data sort of heads towards, say, a 38 metres per second is your design wind speed. But it's been pushed back to what it was previously, so if your 45 metres per second is what they're just stipulating as a regulatory value. Even though the data itself at the moment is sort of not supporting that. It comes down to there was a failure. It wasn't wind engineered per se, or that people have been aware of. So it's the research we need to keep doing and then re-educating both the regulation or regulatory bodies to make sure it's included in that regard.
Yeah, sometimes, I think the wind have a lot of uncertainty. And, at wind engineering, we do a lot of research, doing different analysis. And also sometimes, when we do wind tunnel test, especially in China, we follow building code. And in North America, it's the same. And there's a specified wind speed. And also there's a safety factor to consider to cover some ultimate wind speed may happen in the, maybe, like recently we did one project in Haikou with 460-meter tower in Haikou. In this Wirth, this typhoon just passed by. We just checked the wind speed. When we designed the wind speed by code, they said using 50-year wind speed to design for drift, use 50-year times 1.1 wind pressure to design for strength. This is new Chinese building code requirement. But recently, when we look at the wind speed from this typhoon, we found it's close to 100-year return period. So that is possible to happen, but there's a safety factor, a lot of other study, and we can, come with better solution for that.
I'm not sure what I can add technically to what these guys said, but I'll just, it's an interesting data point. I didn't realize that the typhoon in the Philippines was that far above the design wind speed. As Kevin said, you shared the experience in Dubai and Dr. Du in China. As engineers, we do rely on the data. I think there is some science that we can bring in addition to what we have to date with respect to climate change and looking at modeling of the global circulations and such. But even that doesn't predict a real big increase in wind speed. We can provide the best science or provide our best answer based on the data that we have, and I think there are, as a benefit in wind engineering, there are some things on the structural engineering side, the way that the structural and wind engineers work. There is some benefit there where we look at a relatively conservative ultimate limit state.
我想问一下，就是刚才看到咱们那个 PPT 里面有一个风洞实验是，它是为咱们自然通风系统做的一个风洞实验嘛。就是另外一个就是，如果为风洞实验为咱们自然通风做的风洞实验的话，它的这个设计条件。 比方它的风向风速的考虑，另外一个它的模型比例的一个考虑是怎么去考虑的？谢谢。
Model ratio when you use the model to simulate the actual situation. Thank you.
Thank you for the question. It's well, when we're actually doing when we look at the requirements, so we're looking at an air quality. We're looking at an air quality point of view. So we need to look at how many changes from the external air is going in and passing out again. So it's an air quality point of view in that regard. So that's one of the parameters that we're looking at. The other part is the internal flow velocity. So sort of as a benchmark that we set at is 0.4 metres per second as a minimum we should be getting as an internal flow. The reason we set that is one of the slides I was showing before, the research Ainsley's done, shows that at 0.4 you get about a 1 degree cooling sensation. So you're actually getting some sort of effect. At 0.25 you're not feeling anything from a cooling impact. And then it's sort of been shown that sort of with the draft, and this is where the draft comes in, at about 1 metre per second you start getting papers and so forth on your desk start to ruffle. And we've done some field measurements where when you start hitting those sort of conditions and it's a cooler time of the year, people start complaining from a thermal comfort point of view because it gets too cold. So we always set sort of as a minimum 0.4 metres per second for internal flow, and also depends on the development and the use, but typically it's around about 2 or 3 air changes for a circulation point of view. With regards to the model, so the wind tunnel model itself, the scale essentially depends on the building itself and where it's located. In the cases I had in the 2 case studies, they're at 1 to 300 scale. In the global change building I was talking about, that was at 1 to 250 scale. The reason why was just there was a lot of low-rise buildings around that case, and we're concerned more about the topographic effects. that were nearby. It was just a large ramp up to the site. So it really depends on the building to make sure we're getting the actual flow regime around the building accurately modelled.
Great, thank you.
Hi, this is a question mainly for Kevin, I think. I'd be interested to know your views on whether clients and investors are happily investing in natural ventilation in tall buildings, or whether they're still a bit reluctant and too eager to go back to sort of the easier version of air conditioning.
Sort of, it's a bit of both. I guess the big drivers don't come from a regulatory point of view. One of the perfect case example, this is where it comes down to you can have natural ventilation, but if you don't have some sort of science to support it, it's not going to work. So, the discussion we had was a couple of years ago, we talked about, look, a building that's designed for natural ventilation, it just works, that's it, and walk away. We need to start coming up with more field measurements to actually support it, because when we have that, and that's sort of the feedback we're getting from regulatory bodies saying we want proof that what you're modelling is working. So it's all well and good that we know it does. They want to see it against real-life situations. From a client point of view, I mean, we recently worked on an industrial building where they just said, look, we've got power restrictions on the site. So the natural ventilation, they had someone do a natural ventilation model, which they didn't believe. So we went in as a third party in that sense. And we looked at from the heat loading from all their packaging plants, the flow through it, and then optimised where the openings were. So they took it up because they knew long term they get the benefit out of it. But some clients are looking at it from a point of view of we can sell more apartments if we know, we can push this whole fact. Whereas others are simply going, I've got to tick a box, so I'll do it because I've got to tick a box. So there's sort of two-prong attack. You can educate the client in that sense, and you can also, we need to, I think, educate the actual regulatory bodies to understand what it is and how it actually works, because that will, in the end, push things in that sense.
So I have two questions. One is, if based on our experience of physical model test, under the condition, same height and same volume, and if we increase the number of sides, say triangular, square, pentagon, hexagon, dodecagon, and so forth. So the circular is showing the lowest drag force and also fluctuating component the smallest. So one question is based on the method, isn't it possible? Is there any possibility to converge to a same shape, always go into the same shape? So this is one question.
So, just to answer that, the constraints avoided to go to that one. That's we start with the circular and we could stop right there because it's optimal for the drag and the lift. But the architect does not like a circular building, so that's a constraint. So we got to move to a square one and try to make that, for this example, corner are rounded, and then you play with the resets, and everybody knows how those insets in the building corner can reduce the overall loading. Okay.
So another question is, there are many objectives, and so very simple example, the earthquake and the wind. When we design against the earthquake, the building should be flexible and lightweight. But for wind, massive and rigid structure is better. So completely opposite direction we should go. So in that case, if you find some optimum situation, that situation can be bad for both. So in such case, it is possible to be said the optimal situation.
This optimal design was for wind.
Yeah, but
so later on, somebody can design it for earthquakes, and then these two guys can merge together and then decide between them which is optimal or not.
But we can say that the result is bad for both, so not good for both. Right?
I don't think that will happen in this case because you are optimal.
So in that case, one solution is sacrifice one objective and make it flexible and lightweight, and then we use damping devices. Of
course, those are going to be extensions, but we got to begin to learn to walk once we can do that, then all those icing on the cake will come. Of course, I agree with that. But right now, this was only focusing on the wind part, and it should do a good job for wind. And for most tall buildings of this type, I think wind is the one which governs, as was mentioned in one of the sessions earlier. So I think it would be no problem. There could be some local spots where earthquake could cause a problem. But I think that you are reaching to something which may happen in 20 years. This is just a beginning. We could make flexible and put damping devices, of course. And another thing is that the structure could deform like submarines. There are submarines which do that. And so we could have the shape morphing also at the same time, which is possible. So,
as an architect, I have a very rudimentary sort of or superficial perhaps understanding of the presentation, but in terms of I think what I understood with your optimization method with these optimized plans, the end result then was an extruded building based on this optimized plan. So my question is basically, what do we need to do then to conduct that same kind of optimization into a 3D form? Would it essentially mean having to take a sample of number of floors, etc.? I think you understand. If you can.
Yes, I understand the question very well. Again, as I said, we are learning to walk, and this is the first year of the project, and this will become 3D. And of course, at each level, there would be we have to rotate it in a different way in order to come up. But then again, the constructability and the constraint by an architect or the owner may not allow the building to change that much shape. But no, this is a very well. Is
that a correct understanding?
Oh, of course.
That we would then just take a number
of
slices.
Right now, we're using one slice as an example and extending it all entire the building. It could also vary along the height of the building. You very well understand it. Yes.
It's a very interesting, presentation, and some of the capacity which you presented, 10 kilometers radius and 10 centimeter resolution. Yeah. Is it all over 10 centimeter resolution?
No, what it allows us to do is we can look at the 10 kilometer disk, but retaining that model is then actually come into a target building, but still have it within the context of the 10 kilometer model. And at that point, we can go then down to typically about a 10 centimeter mesh size, which at that point on certain buildings we're running something slightly over 1 billion cells to look at that. But the problem obviously you have is that if you stay on looking at a building at 1/250th scale or even a 300th scale, by comparison the mesh size is like sort of 3 meters. So there's a lot of difference between the center points of those in terms of actually what's happening on the building as we see. And also picking up on the point that the professor was talking about in terms of morphing different shapes is actually understanding that maybe that the profile of natural ventilation inlets need to be different on the 104th floor than they are on the 44th floor. So maybe it's a building which actually slightly changes shape as it rises to allow for wind speeds and different conditions, and maybe with different facade material, because different facades are obviously slipperier and some are more rougher than others, to allow that wind flow through there. So again, we can look at that with detail. And it comes from, and the Professor made a point, yes, okay, we have some very big, powerful computers, and that's like kind of the legacy of having worked in Formula One, because they paid for all that. Architectural projects don't, I'm afraid. But even so, that aside, they are there, and so we're using that as a legacy. But it does allow us to get down to such minute detail as looking at the particular detail of the end plate on a race car front wing, which is it's very similar to looking at the profile of inlet. Natural ventilation inlet, should we say. It's a profile, it's a shape, it's a vein.
Just a very quick question about have you really think about the solar radiation, solar heat gain, in terms of the CFD simulation? As we know, the Soddy effect actually very influential to change the pattern of the ventilations. In certain range.
Yeah, there was a project which actually I couldn't show, which actually ran for a firm of architects on a project in London, and that also took into account solar gain at different levels of the building, different times of the year, different times of the day, according to where the sun was and which aspect. So the people sat by the window didn't roast and the ones in the middle weren't freezing and vice versa. So yes, that has also been modelled in terms of gain as well as ventilation and heat gain within the building and how the air and how that is dissipated through the extraction.
That's great. Yeah, that's definitely one of the key issues. How to coincident to make sure quite a lot of the different aspects they are working together. Because we know sometimes we simplify the model, the result may be too simplified, so we can't actually get the right outcomes.
Okay.
Anyway, thanks.
Yeah, I agree. Thank you.
I guess I have a couple of thoughts that might help to shape the discussion, and I'll put a question first to each of our panelists to try to give a short answer to, even though it's maybe a big question. But I'll ask it in two separate ways. How can wind engineering be better leveraged in design? I'll ask it that way. Or, depending on your perspective, what are the impediments to broader application of wind engineering and design? You can take that question in either way. So maybe I'll start with Peter, if it's okay. Are you making notes? So maybe it's not fair.
Yeah, this is all. Give the others plenty of time to think. I think that wind engineering can be how it can be incorporated into design, and certainly what our experience on CFD is that we're running several different options of a design. In fact, there was a case in Shanghai, strangely enough, not very long ago, where there was 4 different options for a facade design on a refurbishment of a building. So we were able to run all 4 models and say that actually A, B, C, or D, which is the more effective, and say, well, actually D is the better one, but if you did this, it would be even better. So I think that at that point, early testing of that nature, certainly where we can influence, I think the wind engineering is influencing the design. So that when you go to the wind tunnel for the testing, you actually go to the wind tunnel with a much more complete design that you actually of a structure that you actually want to create, rather than going to find out the base detail. So certainly we are doing that. I don't think in terms of the impediments, then maybe as the professor said, perhaps we're lucky we've got this huge computing power, and it's quite scarce, but I guess more people will have that power available to them, or perhaps we'll develop it in such a way that we can actually have all those runs without actually soaking up so much power. But as far as we're concerned, say we run these things in a couple of hours or overnight, and design iterations are done certainly within a day of a model, so it's a very high-speed turnaround. So maybe the constraints on this is the ability of the programs to run and give you the answers quick enough and in a viable way, so that actually it's cost competitive and it's not prohibitive to go down that route. And I would add, actually, at the moment it isn't, but that's obviously also a constraint.
It's really good that we participate in this kind of conference. Most of the time I go to wind engineering conference, the wind engineering, stay together. There's no architects, no structure. I think it's really like, when you go into the design, a lot of time when wind engineering got involved, it's already pretty late, because the architects already make a decision of the building shape, of the function. So I think it's really, we make people aware wind engineering is important, and then we can get involved at the early stage of design. I think this is wind engineering at the early stage consulting is critical for wind engineering to provide valuable input to the design society. Another thing is for CFD. I think CFD is really important direction we go, and we do a lot. Today Professor Ahsan already shows a lot of interesting stuff, and Peter shows a lot of CFD simulation. We have done CFD study, and I think this is the direction wind engineering should go and develop some kind of demonstration database, and people can use. And then when they look at wind engineering, they say, okay, we can go to the database and select the shape. But eventually, I think still wind tunnel will have to increase the efficiency and accuracy. Like today, the Philippine, the Mr. He's not here. He said the wind is really high, and how do you make sure the design is safe? So I think we still have a lot of study to go.
Thank you. Yeah, probably just going on from what Dr. Du just said, it's a big thing. It comes down to when engineering, I think, needs to get involved at an early stage. Too often, we're, I think, brought in sort of a last-minute thing, just sort of a tick-a-box sort of solution. Just going on from what I was mentioning before with the Greenland Centre project, we got involved early on with that design and looked at the, just like from, for instance, from a massing point of view. So I looked at the actual massing project and able to optimise the structural loads on that before we get in too far down the track and reduce the loads by about 10 or 15%, purely based on optimising their building form with a few modifications to it. I think the big problem is when engineering is still viewed as a black art. I've got a lot of people who say from architectural side of things to client side of things, and that's what they say. I mean, perfect examples, even my wife, when people would ask me, what do I do? And I say, I'm a wind engineer. My wife, as I start to explain, my wife just sort of looks at me and goes, I'll explain it for you because I've figured out what he actually does. No one else can quite understand. So I think it's always viewed as something that's highly complex, whether or not it's just a stigma that's put on our industry. We need to be becoming a little bit more open to clients and also to fellow colleagues, so we actually end up getting a holistic approach to the overall design process. Again, for the second part of the question, we were actually speaking with Peter before, because early on I was actually looking at, and that's why he was mentioning about this diffuser design. I looked at diffuser design for a Formula 3 car. Now I think what I sort of get out with that is we need to not just always look at an engineering approach. Too many times we get stuck in one viewpoint. Same as architectural sort of things. You might look at certain architectural firms get stuck on one particular design direction, that is their company policy. Same as with us, we have a problem, we treat it with the same solution. I think we need to start looking at different ways. I mean, even just since I was involved well back, they came up with the blown diffuser. So whether there's things that we can, whether, for instance, from your firm, where they can incorporate side industries and bring it into the way we look at treating buildings. So don't always look at, I always got told that a building, an aircraft, when I was originally doing research, was looking at the planes moving through a wind space, whereas with a building, the building's the one that's stationary and the wind moves over it. And a car, similar car, you're trying to do, an aircraft, try and make it go up, try and make it go down. So we need to, I think, look at different industries and how they can relate back to each other to provide those different options. Because I think that'll be a key direction as to how wind engineering can start to adapt with both the language with clients and regulatory bodies and so forth, and also just providing different avenues of approach.
Yep. Thank you. Professor Kareem?
I think we got to start from earthquake engineering, which is very much fused into a design process. Every design engineer knows, because the loading is very simple. It doesn't depend on the shape of the structure, or it depends on the mass distribution, and every design engineer knows the mass distribution. And then we have earthquake time histories, which people use to check their building for, say, 90% of El Centro or other earthquake records. And most softwares run this time history analysis. You already got model of your building in there. You need to excite that building by then. So the wind engineering, as was said, seems quite complicated, but I think we can make it more as a daily tool for the designer if we provide them tools. We ourselves, our lab, we have provided a database in collaboration with Professor Tamura, which offers you a preliminary design of building, and many designers use them. You don't have to know random vibrations, or you don't have to know the details. All you need to press buttons. And I think if we have more tools like that, especially coming from wind engineering consultants available to people, I think that would help to infuse more of wind engineering into the design practice. Another thing is open source. We are electrical and computer science people always do open source. I develop a code, I put it on the web. If you change anything, you have to provide it to everybody else. So that's how the Linux system, which is the heart of all computing system, was not designed by one person. It was is a shared crowd contribution towards one of the most phenomenal operating system in the world. OpenFOAM in CFD is one of the free software. But it doesn't cost you anything. You can start using it as compared to Fluent. But the difference is Fluent has some upfront user-friendly interfaces which help you to do that. OpenFOAM does not provide that, but many people have developed for those. So I think if you provide more easy-to-use tools in the hands of the designers, then I think wind engineering will infuse more into the system, as opposed to currently, we got to go to wind engineering consultant, so that's a barrier. Can we avoid that? I keep on hearing those questions. So I think if there's a transition which is much more smoother between the two groups, that would help, in my opinion. Yeah.
Okay. Mr. Lee.
我是那个搞那个结构工程师啊。
I'm a structural engineer.
我认为呢，就是我们以前结构工程师呢，按照那个以往的一种经验，也是有效的那个设计了很好的一些完美的一个建筑，无论是在抗风方面也好，或是在整个一个建筑物的一个舒适度方面也好，都是达到了一个完美的一个效果。那么现在呢，就是我们采用了一个 CFD 的手段以后呢，应该讲呢是更加科学，更加直接的那个得到的一个结果。那么应该讲呢，这是对我们的以往的一个设计的可以更加优化。
I think it's a good way to optimize our design. So that's my idea. Thank you.
I think when we think about this vertical urbanism and sustainability, and think about what we're talking about in this context, and we think about the Asian context in cities like Shanghai and Beijing, although we've been really lucky with the weather for right now, we all know that we get these pretty insane pollution in these cities where I don't know if anyone's visited during heavy pollution times. It really feels like the apocalypse. And so it brings into question this idea of natural ventilation that we all take as a kind of given good thing. What I mean is, like, during those in these contexts of heavy pollution, where natural ventilation suddenly becomes this that doesn't. I mean, it's not a benefit anymore, and we have to start thinking about filtration systems and such. My question is. What is the state of the industry, or what is it? Are there ideas? We see a lot of student ideas actually that are quite provocative in terms of using the whole building, using the wind engineering design to kind of drive what would seem to be, at least in a lot of student proposals, passive, global passive systems where the whole building is functioning as a kind of filter, or even driving wind to generate wind turbines for energy and things like this. But on in terms of more on a let's say residential building or something, are there ideas yet in which we could use sort of we could drive wind, let's say, through filters non-mechanically to then create a new type of filtrated natural ventilation for office or housing?
I guess it is a thing that's starting to be coming out more and more, especially with the way urbanism's going. We're starting to get more pollution that's out there. We've had some projects where we actually look at the location to industry, to then look at concentration in parts where we do more of a global model, to see how that concentration spans, to see the opportunity to even utilise natural ventilation, in particular like sensitivity around childcare centres and things like that to major roadways. So it is something that's become a big issue in that regard. How it goes forward treating it, I guess, is something that is very, very early stages. It's good where we start to get actual just conceptual ideas for filtration to actually come apart. But I guess industry at the moment simply just falls back to mechanical. That's the viewpoint that it has. I think it still treats natural ventilation in a sense either as a ticker box sort of thing they have to do, or also it just works and just leave it at that, not even consider it too much. Until we start actually looking at how natural ventilation will actually does perform and get a more of a quantitative analysis for that, then it will start stepping in that direction. Based on some of the flows you can get obviously, because some projects we have been in the Middle East where they've needed to do the ventilation. The big issue comes down with sand filtration. So there's ways to actually filter that out but still allow for the natural ventilation to occur. So I could see similar situations coming about where we look at that from a smog point of view. The airflow, we pump the airflow in. Obviously, there'll be greater from a discharge coefficient point of view, which is how sort of look at from ventilation. So the restrictions on the flow, that will increase. But if we can essentially filter the airflow that comes through, so it will turn into more of a mixed mode solution as opposed to a pure natural ventilation. But I think the end key has got to be a case of, if you do a pure mechanical, this is your energy source, this is what it's doing, because we were talking early on from a carbon point of view, this is what it's doing. So we need to start looking at, if we can reduce it by half, the energy consumption, things like that, that's the stepping in the direction we need to be heading.
Yes, I think I agree with Kevin. It's like in the natural ventilation for some region, you must have a mechanical ventilation as well. Just sometimes you can use natural ventilation to save energy. In China, I live in China now. There's a lot of polluted day. I know that, but China government is looking into different clean energy resources, and then if you use clean energy resources, the environment is going to get better in the future. You design the building, it's going to be like in China. They said you buy a building, you live there, you can have that building for 70 years. Design life is 50 years, but that we are looking at a long time. And if we have the option, everybody can make a step to make the building more sustainable, make the environment more sustainable. And I think it's our wind engineering to look into that direction too.
Now my question for you as what is the next generation? What do you have to offer that is beyond of what we are doing today? For example, one of the things I'm seeing right now in this huge model that you are generating, which is a big models of cities. I think this is, for me, every city, as far as I'm concerned, should have such a model where somebody keep up with it and somebody can use to understand the impact, environmental impact, ethical impact of one building over another. So I think the computational powers that we have today is far beyond what we can do almost. It just makes things unlimited.
Yeah.
So the question is, what is, from a wind engineering standpoint, what is the next generation? What do you have to do?
Okay.
Obviously, tall buildings are wind generators, right? Temperature difference between bottom and top is huge. And we only look at one thing, is a stack effect. But what can we do to make things more positive?
Okay, I'll tackle that first, maybe. Just with respect to the role of the wind engineering firm, maybe in the shape finding, I would disagree with you slightly. I think while yes, form.
I look around, just look around at the conference, right? Everybody doing.
There's a lot of form finding, no, and I agree, and that's.
Not form finding, but people are just creating a building with a different shape and changes every floor, right?
Right.
And also they're creating these shape with the very, very rough edges with balconies and, green architecture and all kind of stuff that the issues that we worry about in terms of vortex shedding issue is becoming less and less. Obviously, there are some buildings that are not being very well designed, but I'm saying in general, people are beyond that point at this time.
Well, I'll share with you an experience that we had recently with a well-known client that everyone would know. We've talked about the rapid turnaround potential of CFD. Well, let me share with you a story about the rapid turnaround potential of working in the wind tunnel, where it was a building that had started with a good form, in that a crosswind loading wasn't an issue. However, working with our client in the wind tunnel, we were able to look at about 25 different shapes, different variations on that shape in the course of one working day. And as a result, sharpened the load estimate, and this is a good performing building that we started with, but we sharpened the overall loads by about 10%. 10% on a 500-meter tall building adds up to a lot of savings. So this as far as potential of looking at looking at that form, even though you're starting from a good point, there's a lot to be gained there. I'm going to turn it over to the panel. Maybe you and I can catch up afterwards because I have some other thoughts. But
yeah, I agree. There's always room for improvement, right? There is always room for improvement, but the question is how much, you know. And if you got combined with a structural system, a good system that can accommodate that change.
I think there's tremendous economies yet to be gained through good wind engineering design. But
we've been doing it.
We agree there, I know. But
Burj Dubai as an example,
yeah.
right, where the wind really had no impact on the design of the tower. Essentially, here you got the tallest building in the world, and wind engineering treatment and proper structural system results with a net wind effect on the tower is very minimal.
Yeah.
Right.
Yeah. I'll let a couple of others on the panel tackle that.
I think your point is very well taken, and I admire the design of Burj Khalifa, its shape. But I think many people also criticize if you go on the top floors, you hardly have one apartment. It is just a spire going up. There's a possibility that we can take the whole base floor to the top floor, and that would be more rental space at the top, so if you make a cone, that is very obvious form to reduce wind loads, but you are losing space also on the top. So I think there may be developments which will come, which will help to carry the whole floor plan to the top.
Just this one example.
Yeah.
I think we're going to hear later in the week too from Carol Willis, who's quite a intelligent lady and head of the Skyscraper Museum, I think.
Mm-hmm.
But our experience in New York recently, now this is one specific economy, but I think design by real estate equation is what's happening with the value of property and square footage being such a premium. As Ahsan said, I mean, there's a lot of value in being able to go to what appears to be not an aerodynamically or wind engineering, an effective wind engineering shape, but there's techniques to still achieve good design.